Hello and welcome everyone. I am doing MTech thesis here under Raghavan sir. So this is my topic, genetic grammars as a formalism for the evaluation of TSP heuristics. So first of all, this is my first formal presentation, so pardon me if I do any mistake or so. So let's begin with the overview of this presentation would be like we would first look at the basics of genetic algorithms. Then we will see what formal analysis has been done today till today in the genetic algorithms, which is known as schema analysis. Then we will go ahead and see what are the limitations in that and what can be done, how it can be generalized, which is known as Formae analysis. And then we will see how it can be applied for the TSP problem. So starting with the genetic algorithms. This is a basic search and optimization technique. It's kind of a modern day heuristic where initially we take the population of randomly possible solutions. They try to recombine. It actually follows the process of natural evolution like in our biological system. So starting from the reproduction, there are two or more parents chosen according to their fitness. Then there is a competition based on the real life objective function. The selection happens, then if they are found to be more better than the previously existing solution, they survive, and likewise the cycle goes on and the generations and generations go on. So as I mentioned, it's inspired by natural evolution, and these are the basic elements for the genetic algorithms. There is a fitness function which is used for evaluation of a solution, of a tentative possible solution. There are reproduction techniques. One is crossover, one is mutation, which we'll see in detail in the coming slides. So starting with the solution of the problem. So given a problem, what is the first step to be done in the case of genetic algorithms? We need to define the solution. There is a solution which is known as the genotype, where each solution or each point in the search space is defined by a set of parameters. So we have to encode it in, it's known as encoding. We need to encode each solution in that according to the parameters they have, according to the features they share or they have. And then they are to be evaluated with the help of fitness function, which is known as the real world struggle of life, or technically phenotype. So in a chromosome, there are different features or different properties for each solution, which are known as genes. Now that genes can take different values. Suppose for human beings, there is eye color, there is hair color. So these are known as genes. They can take different values like blue, green, or whatever the property is. So now the basic or the traditional approach to define formally or mathematically the genetic algorithms is the schema analysis. Now what is a schema? A schema is a partially defined solution. A partially defined solution in the sense we try to group the similar solutions, the solutions having the similar fitness functions, or the solutions which are in one way or the other related to each other. So if we try to optimize the function fx equals to x square with the range 0 to 15. So now fx equals to x square is the objective function, fitness function per se, and so we can encode it in the binary fashion. All the integers can be best. The traditional approach to encode is the binary representation. So we need 4 bits to represent the range from 0 to 15. So let's talk about the schema star 0 1 star. Star means the don't care character. So likewise we can define many schema. In this schema there are 4 other members. Wherever there is a star, we can replace it by 0 or 1. So 2 positions are empty. So there are 2 raised to 2, 4 different solutions possible in that set. So totally if there are n positions or n bits, so totally 3 raised to n schemata are possible, because each position can take 3 values, 0, 1 or a don't care character. And each chromosome is a member of 2 raised to n schemata. Why? Because either we can define a character, we can specify it by saying 1 or 0, or we can leave it unspecified. So this is the very important feature of genetic algorithms, which is known as implicit parallelism, because while evaluating a chromosome, we get to know the information about 2 raised to n different schemata. So this is the feature the genetic algorithm tries to exploit and finds and tries to search for the better solution. So the basic and the fundamental theorem is called the schema theorem. So this is the theorem. It tries to find the membership of a schema in the next generation based on the membership of the schema in the previous generation. So n eta of zeta t plus 1 is the number of solutions present in that set of zeta at t plus 1 generation, and similarly n zeta of t, and this omega represents all the operators we need to apply, crossover or mutation, all other operators. So these operators try to disrupt the schema available. So now the basic thing while looking at this theorem is to note that there is no representation dependence in this theorem, because if the size of the solution set is suppose 100, so there are different mappings possible from the chromosome space to the solution space. So there are actually 100 factorial mappings possible, but there is no way mention of that representation in the theorem. So it basically means that this theorem doesn't depend on the representation. So that's why representation independence. And the next thing is the only thing the representation has to do in the equation is the sigma term. The sigma term is the actual fitness or the seen fitness of that particular schema in the population. It doesn't mean the actual fitness. Actually the schema can have 100 members, but in the current population the schema may have 10 or 15 members. So it is the seen fitness value rather than the actual fitness value. So if to have the correct or the good predictive power by this theorem, we need to see that the variance is very low, because the sampling is happening. So for the perfect sampling to happen, the variance should be very low. So this is the term which actually justifies the sensitivity of the fitness variance of schemata. So these are the things which actually matter with the schema theorem. So now as we saw that the total number of schema for an n, the length of chromosome considered to be n is 3 raised to n. But that arbitrary subsets can be of 2 raised to, here if we consider lambda equals to 2 as we are talking about the binary representation, so it would be 2 raised to 2 raised to n. So there are many possible subsets greater than the total number of schema possible. So we cannot form or cannot represent each and every subset. So there should be other formalism where we can define each and every subset. Let's consider the example of the same problem, fx equals to x square, and let's try to form a subset where we need all the integers or all the solutions which are divisible by 3. So these are the binary representations of each of them, and if we try to define by the schema which contain all of them, then we get the most general one, star 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 star, and which it contains all the 15 solutions. So the variance is very high. We just needed the multiples of 3, but we got all 15 solutions in that set. So that's not a good idea. So now the basic thing we get to know from this is we need the domain specific knowledge. Right now we were talking independent of representation, but we need such domain specific knowledge where we can define the meaningful subsets, not just arbitrary subsets. So in the proposed framework, or this framework was proposed by Radcliffe in 1992 based on the equivalence analysis approach. So where each equivalence class is called a forma. So each equivalence class means a meaningful subset. We'll see how to. And the good thing is the schema theorem still holds. Even if we talk about any random or arbitrary subset, the schema theorem still holds just that we need to calculate the disruptive coefficients accordingly. So let's begin with the grammar. So this is called the genetic representation, where we will form in such a way that each of the equivalence relation will be a gene, and each of the classes induced by those relations will be alleles. So let's try to formalize or define the human generation or the biological thing. So all the humans can be characterized having the eye color of 3 types. This is just an example: blue, green or brown. So we can partition the search space in 3 classes. So now this eye color is a gene, and these 3 classes are forma. Now we can define the intersection of more than one gene or more than 2 genes. So the first one is the eye color and the second one is the hair color. So we can go ahead and define the intersection of them. So suppose the eye color has 3 things: a green, brown, blue, and the hair color has curly and straight. So we can form a tuple of the combination of 1 forma from each, and we can define the intersection of this forma. So now all the notions are borrowed from the linear algebra, so everything is similar to the linear algebra only. So if we try to define the span of the 2 equivalence relation, then it's all possible intersections of any subset of that particular set. So the third one is added, psi EH, which is a intersection of the first 2. In the same way, independence, suppose a set is said to be an independent set if any of the relation cannot be constructed as an intersection of the rest of the others. So the set defined above, the 3-member set, is not independent because we can construct psi EH by intersecting psi E and psi H. So now orthogonal property is like Suppose we have a set of n dimensionality, and if we take one forma from each of them, and if we try to form a tuple, so each such tuple should have at least one member in it. So for this particular set, we have both of them, eye color, hair color, and this. So suppose we take the eye color as blue and hair color as green, and the eye and hair color as brown and brown. So they do not have any intersection. So this is an empty set. So orthogonal defines an intersection property. Now, as taken from the linear algebra, orthogonality implies independence here also. Basis is the same thing. For the basis of a set is when we can find any relation by constructing by intersection of all the others, and if that set is independent, then that set is called the basis set, and if that set is orthogonal, then it is called orthogonal basis. Now, as mentioned, each gene is a basic equivalence relation, and each allele is a basic forma induced by those particular relations. So now let's try to define a representation. The representation is a mapping from the solution space to the chromosome space. So the mapping should be injective. That means from each solution shouldn't have more than one chromosome. Now injective can be defined in this framework as coverage property, where if we try to talk about two solutions, at least there should exist at least one equivalence relation under which the two solutions are not equivalent. Like we talked about three different relations. So at least the two solutions should be different by eye color or the hair color or some other relation. So let's consider an example. Suppose we have three relations, eye color, hair color, and third one you can consider as our property left-handed or right-handed, and we have two solutions, x and y as such. Now the property is dynastic potential. Now dynastic potential is very well as we see in our human life, where suppose two parents are there, and as generally seen, whenever a child is born, we try to identify what characteristics he or she got from the mother and father. We say that the eyes match with his father, or the smile matches with his mother, or likewise. So the thing is, we try to find all the children or all the solutions from a particular set L, such that each gene takes a value from either of the parent, not from outside. So all such children are known as lying in the dynastic potential of that set. The similarity set is the same thing, where to give an example informally, suppose both the parents have some particular interest. So if that interest is shared, the same interest is shared by both the parents, then the child should also have the same interest or the same favorable property. So this is the thing which is mentioned in the similarity set. Now if we try to define the recombination, it takes the two solutions, and with some control parameter it generates or produces another solution. So the dynastic span is again the same property as dynastic potential, where for generation after generation we try to see like what are the different children it can produce. So immediate dynastic span is like taking two parents and seeing in just one recombination what different types of children it can produce, and full dynastic span is like going till infinite generations. So now for a genetic algorithm, the three basic things are there. One is exploitation, which talks about the respect. Respect means, as I said, the child should land up having the same properties. The properties which are shared by both the parents, the child should have their property. So that is called as exploitation, because as we consider that both the parents are favorable in a particular situation. Suppose let's talk about the North Pole. So if they are favorable to such temperature, and both the parents are compatible to that, so the child should also have that good property inherited by her or him. And the other thing is exploration. It is also very necessary not to land up on a local optimum. So it's necessary to explore the whole solution space. So this property is mentioned under this framework as assortment. And the other thing is, as I mentioned, implicit mutation, where transmission is considered, where each allele or each gene is copied from either of the parent. So there is no feature which is taken from outside. Both the parents only constitute the whole solution for the child. So this is the same thing as I said. The respect double implies all the children lie in this parent similarity set. So the other thing is, when we try to consider both respect and assortment simultaneously, that property is known as separability. And when we try to consider transmission and assortment, both things together simultaneously, that property is known as G-separability. And if a solution or a forma is G-separable, then it is by default separable. Now, whatever I said, may not be clear, so let's take an example. A schema which we talked as the traditional approach, which deals with the binary representation. It is orthogonal and G-separable. Let's talk about something which is non-orthogonal, as in our example, TSP. So let's consider two sub-permutation, the two subtours of big tours. So if one tour is 1, 2, 4 and the other tour is 1, 2, 3, so the respect is taking the common properties in both of the solutions. So the common edge shared by both of them is 1, 2. So this edge should compulsorily be in the child. And the other thing is combining two different solutions, because we need to explore the complete search space also. So one edge which can be taken from the first, and the other is we should take 2, 4 from the first and 2, 3 from the second. Likewise, we should combine both of them. But the degree of each city will be only 2 in the tour. It can have only 2 edges. We cannot have 3 edges. So point is, we cannot do simultaneously respect and assortment. So this is meant to be non-separable forma. So generally the kind of forma which are experienced by TSP are non-separable. Now this is a completely different approach as the traditional approach. The traditional approach is like defining the representation, as we did in the binary case. We first defined that we will follow the binary representation, and then we try to find the operators which will suit accordingly. And in this approach, we don't care about the internal representation, that happens to be secondary, and we try to apply an operator and see that operator operates on which particular property. And then we go ahead and evaluate the performance or the efficiency of that particular property or representation. So this is the kind of flow which we need to do. Identify the forma which the particular operator operates, then determine the representation on which it is working, then assess the quality of the representation and predict the performance accordingly. So the traditional approach was totally different from this. So now coming to my particular work where we try to deal with the TSP problem. So there are any TSP problem is actually a tour. We need to find the optimal tour where we need a permutation which is best according to the tour length distance wise. So the three kind of information which are very important are position, in the position of a particular city in the complete tour, whether a city lies in the first position or it lies towards the end, or is it somewhere in the between. So this is a particular representation. The other one is precedence forma, where we talk about the relative ordering between the cities. So if in the particular tour, if a particular city lies before that, or maybe after than that, we don't care whether they are adjacent or not. They may be somewhere else, but the relative ordering between the two. And the third one is the adjacency forma, where we deal with the edges only, either directed or undirected. So as I said, we can the schema theorem mainly deals with the fitness variance. So if we try to plot a graph with the forma order as the x-axis, where I have considered the TSP lib problem, 100 city problem, and the distance measure taken is Euclidean distance. So if we try to the 100 city problem, so there can be forma will be till 100, because a set can have only a tour with 100 cities. So the forma which happens to have very less variance are these three: undirected, directed, or block. Now it is very clear that the TSP function has the objective function as the edge cost of each edge in the tour. So it is very intuitive that the edges will have the lowest variance, but the block is also having the lowest variance. Why? Because when we consider a contiguous subtour, then in that the edges are also included. Because when we consider the subtour, suppose the subtour is of length 5, then 4 edges are there which are inherited. So block is nothing but an indirect way to say that we are inheriting the edges. So these were the different around 12 crossovers we have compared, and these are the things which we define, that on this basis we will try to analyze different operators and we will try to predict the performance of the operators. So these are the different this is the algorithm which I followed. The other different parameters. The problem the results for which I am showing is 100 city problem, which is shown as bold, and these are the different parameters. The crossover probability is taken as 0.7, mutation as 0.05. The population size at any time is 100, and the selection is used as. These are the common genetic algorithm parameters, and we have taken the evolution till 250 generations. So what we did is we just tried to find with corresponding to all the 5 forma which we saw, what is the transmission rates and the respect rates for each forma for each operator. So this is we get, and as I said, the dynastic variance also matters. Suppose we talk about the eggs laid by chicken. So it's not that some chicken will have the eggs the size of dinosaur and some chicken will have this size. What I mean is, whenever we were told to write an essay about a cow, we always wrote that a cow has 4 legs. We never used to think, and we never went to see each cow that is it having 4 legs or not. So the population should have some properties which are common. There can be a difference in their size or shape and in some color and all, but some properties will always there is not much variance. So in this experiment we took 2 solutions and we tried to find 500 different children for that by applying different crossovers, and we tried to find the dynastic span. Dynastic span means the unique solutions. So this also matters. This characterizes the assortment property, that how much broader we can search or how much we can explore our search space. And this is the transmission rate, the operator which transmits more, the operator which takes the properties only from parents and not from outside. So the mutation, implicit mutation, is very less. That particular operator which will perform in a better sense. So this is the final result, where we try to find the optimum tour lengths. So as I said, the 4-5 properties which I listed, when we try to compile and we predict, the result are very good, that we can predict that which operator can perform better than the others, and the comparative analysis we can do very well. So these are the main references. Thank you.